Good morning, people. So, it's not a course, it's a marathon. And you are survivors. Huh? Well, no, it's really nice. And then today is Friday. We have tomorrow. We have classes this morning, afternoon, and tomorrow morning, and then afternoon. Tomorrow afternoon we have a discussion about some possibilities, future possibilities, on how we are going to organize ourselves after the course in terms of networking, in terms of products that we can produce. Okay, and then we will liberate you to enjoy São Paulo for some hours. No? One day and some hours. Now I would like to introduce you Professor Edmo, which is a physical oceanographer that has very strong links with global discussion processes on climate changes, on the effects of climate changes. He is going to introduce himself, but I would like to ask him to come here and share with you his knowledge, and I hope you enjoy and use him to improve your knowledge and make the connections you are intending to do. Okay? So enjoy, Edmo.
Okay, hello everyone. I'll try to find the best, the most comfortable way to teach this class. Okay. From this point, I can see all of you, and I can see my screen. Yeah, I think I'm going to do that. But in any case, can you all see me? All right, so. Okay, I was introduced as a professor at the University of São Paulo, and that's true. I'm a retired professor at the University of São Paulo, but in the past 1 year, I was a visiting professor at the Federal University of Ceará, another state in Brazil, and from now on, I'll be also a visiting professor at the American University of Sharjah in the United Arab Emirates. Actually, I should be there by the moment, but because of this course, I'm only flying next month. As Alex said, I am a physical oceanographer. Actually, I'm a physicist that became a physical oceanographer, and for that reason, I might be a little bit biased towards the physical aspects of the problem, but because of the fact that oceanography is a truly interdisciplinary science, anyone that is doing something in oceanography has to know a little bit of the other aspects, not only on his main subject. So I'll try to, as much as I can, to point to aspects of the problem that are not directly related to what I'm doing, but depends on the knowledge of the physical aspects. And of course, I might not be right most of the time when I try to say something, for instance, on the biological aspects. But I hope you would forgive me if I do that. Another thing that I should mention is, when I was invited to give this class, they said you have to talk about understanding and modeling ocean basins. I didn't understand exactly what that meant. And so far I don't understand. But I will try to talk a little bit about what is there, but in a way that is more related to what I believe would be most important for you in this context. So I'll talk about ocean. I'll talk about how the ocean moves and how the movement, the motion of the ocean interacts with the rest of the climate system and how it somehow affects the biology and the chemistry and the environment as a whole. And again, it will be strongly biased towards the physical aspects of the system, but well, there are biologists around that would complete the subject. So I'm not that much worried about this tendency of mine to be more to the physical side of the problem. All right, so let's start. I'll try to follow this outline. I'll talk a little bit about the importance of understanding the ocean. That's interesting because just a few minutes ago, someone came to me and said, well, why is that the ocean is not part of the main discussions about carbon sequestration in the political arena? And that's something that is funny because if you look at the ocean, if you look at the climate system, if you look at Earth as a whole, the major reservoir of carbon is the deep ocean. Most of the carbon that once was around in the atmosphere is now kept strongly held in the bottom of, near the bottom of the ocean. And today that we are increasing the amount of the carbon being released in the atmosphere, most of it is being captured by the ocean. And most of the sequestration of carbon is being done by the ocean. And even though if you go to these big meetings, these high-level meetings, the politicians talking, they barely touch the ocean. And that's something that we need to be more proactive in terms of bringing the importance of the ocean to the politicians, to the decision makers. So that's what I'm going to do in this first part of the course. And then I'll give a little bit, a very small, very little introduction to the physical oceanography, or the physical aspects of the oceanographic science. And I'll try to say a few words about what is modeling of ocean basins, of what is the modeling of the ocean. What does an ocean model mean? And then I'll talk a little bit more about the ocean and the climate. And this is my main expertise, so probably I'll get a little bit excited when I talk about this. But that's the way things are. When you talk about what you like most, you take more time talking about it. And finally, I will bring a little bit of the South Atlantic into the subject. I will try to focus on some aspects of the South Atlantic that are important to climate or to the environment, not only in regional but also in the global scale. So that's the introduction, and I will now start asking this question. Why should we better understand the ocean? Well, of course, to answer this question, I could be talking for days only to answer this question, because there are too many reasons for us to understand, to better understand the ocean. But of course, I would just pinpoint some of the aspects that I deem as the most important. And let's begin with this. Earth, we translate into Portuguese as terra, the Latin word for the planet. And terra also for us means the solid ground. But if you look at the planet is mainly water in its surface. So there are some people that say, well, we should call it the aqua planet or the water planet or the planet ocean, not Earth. But of course, it doesn't matter if we call it Earth, but understand that this is a place where the ocean plays a very important role. And I'll take your time, and if it's possible to dim the lights or turn off some of the lights, because I'm going to show a little movie.
Earth is the water planet. Although 40% of Earth's population lives within or near coastal regions, the ocean impacts people everywhere. Most of Earth's water is stored in the ocean, a driving force for weather and climate. The Earth's surface is warmed unevenly by the sun. Heat, a form of energy, helps drive ocean and atmospheric circulation. The ocean absorbs and stores more heat than the atmosphere. Both the atmosphere and ocean move heat. The atmosphere does this quickly, the ocean slowly. At the ocean's surface, winds drive currents. Multiple forces keep the global ocean conveyor belt, or thermohaline circulation, in perpetual motion. Below the surface, deeper currents are driven by differences in density. Mixing and upwelling in the ocean, transport nutrient-rich waters to the ocean's surface. Nutrients sustain biological productivity in the ocean. Extreme variations in sea surface height and sea surface temperature affect ocean and atmospheric circulation. El Niño and La Niña occur when changing wind patterns displace warm and cool water in the equatorial Pacific. Both have global impacts. During either of these events, the replacement of cold water by warm water leads to air temperature swings and changes in humidity. This alters weather patterns by steering storms and rainfall to new locations. Shifts in rainfall affect plant growth and areas impacted by drought. When heat is exchanged between the ocean surface to the atmosphere, it influences climate. For example, heat and moisture carried by the Gulf Stream northward bring warmer temperatures and a moderate climate to Europe. An eddy is a circular moving body of water that spins off a main current. Eddies play a major role transporting heat and nutrients. Thunderstorms are a frequent occurrence in the tropics. Some of these may become organized into large rotating systems with strong winds growing into tropical storms or hurricanes. Tropical ocean basins like the Caribbean and the Gulf of Mexico retain substantial heat, making these regions favorable for rapid storm intensification. By extracting large amounts of heat from the ocean, storms can become massive and destructive hurricanes. A driving force for weather and climate. The ocean is essential to life on Earth. It is the primary storehouse of Earth's water. Without the ocean, our planet would be uninhabitable. NASA satellites and their unique view from space are helping to unveil the vast and largely unexplored ocean.
O resto agora é propaganda. Na NASA não podemos parar, apesar de eles merecerem, né, os créditos. Mas o que vocês viram aqui, possivelmente algumas coisas... Oh, I'm sorry. All right. I was so absorbed by the movie that... Oh, all right. But wait a minute. It's been more than 3 days that you are all along should be speaking Portuguese. Huh? All right. Okay, what I was saying is that, well, first I said that NASA has its merits, so we should give a thanks for NASA providing this movie. But when I was speaking that you interrupted me, I was saying that most of what you saw in this little movie is about what we are going to talk in this course. So if you didn't understand most of it, you will understand a little bit more afterwards, I hope. And that's the reason I showed you the movie. The next time you watch it, you probably will have a better understanding. And the movie is going to be kept on the site so you can download it and watch it afterwards. Okay, let's proceed. One thing that was mentioned in the movie is that Earth's surface is mostly water. Almost 3/4 of the Earth's surface is water in a layer of about 4,000, 5,000 meters deep. That means that it's a very large amount of liquid water covering the planet. And this is very important, as I will mention in the remaining of the course. But one important aspect is that the high heat capacity or the high specific heat of water makes that the ocean is the memory of the climate system. So the climate system and the planet, it varies, but it varies in a rate that is slow, allowing for life to exist and to be sustained. And that's because the ocean is the memory of the climate system. I'll mention more about that in the sequence. And as I said, the ocean stores 1,000 more carbon in the atmosphere than the ocean. Actually, heat, 1,000 more, and 50 times more carbon. Okay, what is the climate system? The climate system, probably you have been listening, hearing about this during the course, and there are different aspects, different views of the climate system. But for us, oceanographers, we see the climate system as a component, a conjunct, or a combination of different aspects or processes in which the ocean plays an important or a very important role. Or the ocean is a key component, because if you take the ocean out of the system, you would change this dramatically, much more than if you take, for instance, the volcanoes, or if you take out the human being, or if you take out lakes or rivers. But if you take the ocean, the change will be dramatic, as I will mention in the sequence. Okay, again, the ocean is the regulator of the climate system. If you think of the climate system as an interaction between or among different components, the ocean is important, is a very important component. But also, it is part of the system, and then it is also affected by changes in the climate system. So when we talk about the ocean and the climate system, we have to think in terms of what does the ocean do to the climate system, and what are the feedback of the ocean to the climate system. So once the ocean is affected, what does it do in return? This is something very important, and I'll mention it again. So just to summarize the importance of the ocean in the climate system, you all know about the IPCC. The IPCC is an international panel that is nominated by a very large amount of countries on Earth that from time to time get together and analyze the knowledge, all the knowledge that is present at that moment in terms of climate and climate change. And I'm saying that because I know that there are some people out there that says, well, the IPCC is a bunch of people bought by some conspiration or whatever, and there is no climate change, or if there is any change, it does not have anything to do with we human beings, or we are not in any way guilty of any change in the climate. So I don't think so. I think that the IPCC is a very serious group of people that tries to do the best they can in terms of understanding what is going on and giving a contribution in terms of what should we do in terms of understanding, mitigating, and if we can't solve the problem, how can we adapt to changes that are coming inevitably. In this graph, what we show is the emission of carbon in the past 200 years. So it started the Industrial Revolution in Great Britain, when by that time no one would care about burning coal or burning petroleum. So there was practically no human contribution to the amount of CO2 or the carbon dioxide in the atmosphere. So afterwards, it starts increasing. And this black line, that the most prominent line in this figure, shows the increasing of the total anthropogenic carbon in the climate system. And as you can see, I hope I can, okay. If you look at this curve here, it increasing, and if you understand about derivatives, if you take the derivative of this curve, it's positive, and if you take the second derivative, it's also positive. That means it's something that is increasing in an accelerated way. So the rate of increase is increasing with time. This is very bad news, because in nature, every time you have something that starts to increase, there are some mechanism that makes that the second derivative be negative. That means that it's increasing, but it's increasing in a decelerated way. So the rate of increase decreases with time, and there will be a moment when it gets to a maximum and then decreases. That's what nature does normally. In this case, it's not what's happening. The rate of increasing is increasing, and this is very bad news, and it's only possible when you have an external agent in the system. And nature is the natural thing. And what is external in this process? I'll give you a candy if you can guess who are the external agent. Because before human beings, there were several moments in the system that change happened, but there was no one burning coal or burning petroleum, gasoline, or whatever, putting fire on forest the way we do. So we are the extra element in this mechanism. Uh-oh, I have to go. Yeah, that's another slide from the last IPCC report, so the AR5, in which for the first time, I think that was the first time the ocean really got into the IPCC assessments in a very strong way. Because before, the ocean was mentioned more or less, well, the ocean is, but from the AR4 and AR5, that was the last one, the ocean was really in the center of the attention. And that's because if you look at this figure here, this is indicating the increase in temperature on Earth's surface in the past from 1901 to 2012, that's about 100 years. There was an increase of up to 2 degrees Celsius in certain regions. And I don't need to be talking a lot about what the consequences of it. I will talk a little bit more in some slides ahead. Okay, so, and so what? Okay, the ocean is being affected by climate. The temperature on Earth is increasing, but should we bother about that? Should we be worried about that? Yeah, of course you have the answer, but I'll talk a little bit more about it. We should, because to begin with, 70% of our planet is covered by water. And if this water gets warmer, there will be consequences. And if you think in terms of the human population, more than half of the human population live along the coast, along the shorelines. And if you, for instance, increase the sea level for about 1 meter, that would cause a very large amount of disaster, not natural, because this is human-induced. There is another thing that is not so well known. It's the thermohaline circulation. In the movie, there was something about this. And this is going to be something that I will talk very, I would say, not most of the time, but I will pay a very important attention to this phenomenon in the sequence of this course. So for the moment, I just introduce you to the thermohaline circulation, or the global conveyor belt, or the global thermohaline conveyor belt. I'll talk more about this feature. And this is something that you have been hearing, listening most of the time, is that if you change the temperature, or if you change the conditions in one specific system, for instance, in the ocean, you have lots of consequences, like affecting the fish metabolism, the growth rate of the population, the reproduction, the productivity, migratory patterns, susceptibility to diseases and toxins. Any small change in one part of the environment will have very strong consequences. And the ocean is a place where we are very much worried about, because changes are already happening. I don't need to be talking about this for too long. Everyone knows that if you have warmer temperatures, you have impacts on fisheries. And for us here in Brazil, fisheries are not that much important, because our waters are not that much productive. But if you go, for instance, to Western Africa, or if you go to the Indonesia, or if you go to several other places on the planet, fisheries are one, if not the most important source of food for the population. And if you change a little bit, you can have dramatic impact. There are some studies, for instance, showing that some changes are happening. There are several kinds of fishes that are moving northward. They are adapted to live in a certain environment, and then the temperatures start to increase, and they try to find a way where they can survive. And the way they find is to go to somewhere where the temperature is about what they are adapted, or they are used to. And that's northward, in direction to the pole north, in the northern hemisphere. That's because this is a study done by someone on the northern hemisphere. But if you are in the southern hemisphere, I would say that they are moving southward. And that is something that is happening, but mainly in the North Atlantic. I would show you why in a later slide. Oops, I have to go this direction. Another aspect that is happening to the ocean is the acidification. As you know, any substance can be acid or basic. If it's acid, it has more, some more molecular, some radicals in it, or if they are basic, there are less of it. One is more negative, one is more positive. This is something that the chemist could explain better. But for us, what we should know is that if you start putting more CO2 into the ocean, it's going to be more acid. if it gets more acid, it will interfere, for instance, with the formation of the shells in the shellfish. Any of those little bugs in the ocean that has a shell or has some sort of skeleton, they will be affected because in acid environments, forming a shell from calcium and carbon is going to be much more difficult. So you would impact drastically the coral reefs and the formation of shells of these little bugs in the ocean. And of course, this would have a very large impact on biodiversity. And of course, we could be talking about this for a long time, but what matters at the moment is that the ocean is getting more acid because it's getting warmer and with a higher concentration of CO2. And once it gets warmer and has more CO2 dissolved into the waters, it's going to capture less carbon, releasing or allowing for more carbon to stay in the atmosphere. And with more carbon in the atmosphere will get warmer, and then the ocean is going to get more acid and warmer. And then this is a kind of a positive feedback process. So the more acid it gets, the warmer it gets, more CO2 in the atmosphere, and warmer the atmosphere, warmer the ocean, and more acid it becomes. And then in the end, you can imagine what could happen. Well, there are other impacts. If you start having more storms, or if you have the ocean surface to being higher, you start getting impacts on ports, or you start having more ocean disasters with ship collisions or ship getting having problem in ports. And well, I don't need to be talking about this for too long because you can imagine the consequences of a warmer and higher ocean along the coast. So, in order to understand the role of the ocean in all this, we need to have a better understanding of the physical processes. And for having a better understanding of the physical processes, I would give you a little bit of physical oceanography. Well, oceanography is, as I said, a multidisciplinary discipline or science. The oceanographer has to understand well the physics, the biology, the chemistry, and the geology, but in a way that is not, for instance, what a marine biologist does. A marine biologist is someone that studies a bug or an organism that by chance lives in the ocean. A marine chemist is a guy or a girl that studies some substance or elements that is found in the ocean, but they don't need to correlate that with the other components of the discipline. A marine biologist is different from a biological oceanographer. A biological oceanographer is someone that when he or she finds an organism in a place, she or he will try to answer questions such as, why does this bug live in this place? What are the relations or interrelation of this individual with the rest of its environment? And what happens if the water that is moving this direction starts moving in the other direction? What would be the impact on the organism? And so on. So the oceanographer is someone that has to be also looking for the different aspects of the science. So There is a difference. For instance, at the University of São Paulo, we have the Oceanographic Institute, in which we have physical, biological, chemical, and geological oceanographers. But we also have a Marine Biology Institute that is for biologists that are studying organisms for the ocean. But of course they care, but not that much in terms of the interrelation of the organism with the environment. But in this discipline here, we are more focused on the physical aspects of oceanography. And in order to understand the physical domain, we need to start thinking about what is the ocean? Well, the ocean is a very large volume of water that is not still. The water is moving around. And the movement plays a very important role in the entire process. So the question is, okay, the ocean moves, the ocean circulates. Why? What are the causes? If you were born, let's say, 2,000 years ago, the answer would be quite easy. Oh, the ocean moves because there is a God that when he gets pissed off, he would just blow up and bend a storm would surge. And the same for the atmosphere. There was this Aeolus guy that would blow and the wind would, the atmosphere would move. But we don't live 2,000 years ago. We live 2,000 years after that. Well, there are still some people that believe in this, but we don't have to think that the movement is done by these gods. There is another god. There's another god, the sun god. This is the one. All the movement that happens in large scale or small scale in the atmosphere and the ocean are, in the end, done or happened because of the sun. The sun is the primary energy provider for the movement or the motions of the atmosphere and the ocean. And this is kind of a very simple thing that has some complications, but can be summarized more or less like this. The ocean or the earth as a whole is warmed by the sun. The earth is a sphere. Oh, there are some people that don't believe that. I know that you probably have heard of the Flat Earth Society. It's a group of people that believe that the earth is a plane. It's a, I don't know how, but no. For us, in order to understand what's happening, you have to take this model, because otherwise it's very difficult to explain. So the earth is a globe, and the sun is very, very far away, in such a way that the sunlight, when arrive to Earth, they arrive in parallel rays. And because of the curvature of the Earth's surface, the insolation is different. If you are in the equator, in the tropics, you get much more insolation, or the efficiency of the sun is higher than if you are in the higher latitudes. That's because you have a distribution of amount of energy by the area that the light arrives. So you have much more concentrated energy near the tropics than near the poles. This is quite easy, as it's shown in the figure. Try to explain that it's in a flat Earth. Okay, because of that, in between the tropics, if you go from the Tropic of Capricorn, that is more or less nearby, to the Tropic of Cancer in the northern hemisphere, between these two latitudes, there is a gain of energy. The Earth receives much more energy than it releases back to space. So we have a surplus. We have a superavit. There are more energy. There is a net radiation in our tropical regions. If you go north of the Tropic of Cancer, or if you go south of the Tropic of Capricorn, there is a loss of energy to space. So the Earth loses heat to the space in higher latitudes and gain energy in tropical regions. In such a way that, actually I should talk a little bit about physics. There is a law in physics, that's a law of Stefan Boltzmann, that says if a body gains heat, it warms up, it gets warmer, until a point where the temperature that the body reaches is enough to send back the same amount of energy that it received. So in the equilibrium, anybody that is receiving energy will be releasing energy in the same amount, and for that it has to have what we call the temperature of equilibrium. The lay of the Stefan Boltzmann law says the amount of energy necessary to get a body in equilibrium is sigma equals to, or actually the energy is equal sigma times T to the fourth or the fourth potency. This T is the temperature of equilibrium. That means that if any body is receiving energy, it has to get warmer until it gets to an equilibrium. If it receives more, it will get warmer in order to reach a new equilibrium. If it gets more, it gets to get warmer, and so on. And that's what you should think about in this figure here. In the tropical regions, there is a net gain of energy. The Earth is gaining heat in the tropical regions. Why is that we are not getting warmer, warmer, and warmer as time goes on? On the other hand, in the higher latitudes, Earth is losing heat. We are getting more, we are sending more energy to space than receiving from the sun. So in higher latitudes, the temperature should be going down and down and down. And that's not what happens. And the answer is easy. Well, somehow the excess of energy from the tropical regions goes to the higher latitudes in order to compensate the loss in such a way that the total balance is in equilibrium. It's more or less like, for instance, two brothers. One is a very conscious person that spends less than he gains, and the other one is, on the contrary, someone that likes to have fun and spends much more than he earns. One gets richer, the other one gets poorer. But because they are brothers, they love each other. And somehow the one that gets more gives to the other that has less, in such a way that the amount of money between the two remains constant. And that's what's happening here. The higher latitudes gain more heat and somehow sends those heat, the excess, to the higher latitudes. And can you guess who does this? The ocean and the atmosphere together. In the lower latitudes, the ocean is the most important. The ocean gets heat from the tropical regions and brings it to the subtropical frontiers. And from that point, the atmosphere takes the excess heat from the ocean and redistribute it for the atmosphere in such a way that if you take an integral of surface around the Earth, the total amount of energy that's arriving from the sun is equal to the amount of energy that is being lost to space. And the ocean and the atmosphere are the responsible for this kind of redistribution. In the ocean, it is the most important agent in the tropical regions. I will talk more about that in the sequence. Just a little bit about the atmospheric circulation. I would change the slides a little bit faster in this point because, well, this is not a class on atmospheric circulation. But we need to know a little bit in order to understand the ocean. My question is, we have 1.5 hours of class and then a break. Is that right? So we have still 35 minutes to go before the break. Okay, the atmosphere, the motion in the atmosphere can be summarized more or less like this. If you have a heater in one corner of a room, it will warm the air there, and the air in that part would get lighter and rises. And then when the air rises, it creates a vacuum that needs to be filled. And then the air from other regions come to near the heater. And this air that goes up eventually goes to fill the air that came to fill the one that rises here. And then it ends up with what we call a convection cell. It's a cell that is driven by a convection system. The atmosphere is completely similar. You have the sun heating Earth in a differential way. The tropical band, there are much more insolation, and so the temperature gets warmer in those regions, the air rises, and then there is a circulation pattern that results from that. Along the tropical or the equatorial band, all around Earth, there is a band of nebulosity that is named the IPCC, or the Intertropical Convergence Zone. This is a very important region that is related to rain in the Brazilian Amazon or in the Indonesian or in several places around Earth. As I said, this is not an atmospheric science class, so let's move on. These circulation cells resulting from high or low pressure zones that moves the atmosphere, if happened in a planet that is spherical but does not rotate and has no continents, would be something like this. Air rising in the tropical or equatorial region, going up, and then in the higher levels of the atmosphere would go towards the poles, and then would sink and come back into the equatorial regions. So these would be kind of interhemispheric cells. And this would happen if Earth would be standing still in space with no rotation. But we know that Earth rotates, and we also know that Earth has continents. And because of the continents and rotation, these are much more complicated. And this is what happens in our planet. And what I want you to take it in your memory from now on is that because of all this, there are some wind patterns in the planet that are very important. The winds near the surface are such that in the tropical regions, they move from east to west. And these are the trade winds. The trade winds are winds that blows in the tropical regions from east to west, both in the northern and the southern hemisphere. These are the northern trade winds, these are the southern trade winds. And in the subpolar regions above the Tropic of Cancer or south of the Tropic of Capricorn, the winds blow from west to east. They are named in English the westerlies, winds from the west. So in the entire planet, in general, winds blow from east to west in the tropical regions and from west to east in the subpolar regions. These are very important wind patterns, and the ocean circulation, the way it is, depends on this wind pattern. This is a summary. You have winds from mainly, predominantly from east to west, the trade winds, or the west to east in the subpolar. And of course, near the poles you have other parts. But let's only talk about the subtropical and the temperate zones. Again, if you had no continents and if you have continents. When you have continents, things are a little bit more complicated. But I don't want to complicate too much and go directly to the ocean. So the ocean is, as I said, a very large amount of water that is moving. And the motion of the ocean, or the ocean currents, are one thing. They are happening. If you go there, say, oh, the ocean is moving. But the ocean moves. If you, for instance, don't have much time and stay there only for 1 hour, probably going to see some wind waves, some very high frequency movements. If we have a little bit more time and stay for too long, and then probably we're going to find out that there are some motions or movements that happen in a much longer periodicity. And if you have even more time and stay there for, let's say, for 1,000 years watching the ocean, and probably we're going to see some motions that have periods of about centuries or 1,000 years or more. So the ocean is moving, and for understanding it, for studying it, we usually divide the motion as the upper ocean motions, or the upper ocean currents, and the upper ocean, I mean, in the upper 400 meters. And in this region, the wind is the main driver, the main agent, the main source of kinetic energy. And if you go to the deeper regions of the ocean, it moves in a much slow rate, but it moves, in the causes of the movement in the deeper regions of the oceans are what we call thermohaline gradients, or differences of temperature and salinity, or differences in density. We are going to be more specific on this in the sequence. Well, the movement, the motions, the currents in the upper ocean is something that is being known for a long time. If you go past in history, for the first time man started to going into the sea, he started knowing that the ocean moves. For instance, the Vikings, we know that they started from here, from the Scandinavia, and came to Iceland, and then from Iceland they came to the Greenland, and then there are some indicators that show that the Vikings arrived in North America. And this is more or less what they did. They would start from this point and navigate to the west and then return along this line. This is something that today we know from studying some sort of records. But the question is, why did they do this way? Why didn't they come this way and go back that other way? Of course, probably they tried. In the end, they started doing what was best. So they had this sort of empirical knowledge of the ocean circulation. And not only the Vikings. Christopher Columbus, or whatever, what's his name? Cristóvão Colombo, or Columbus, or Colon, or whatever. This guy started in Spain because the Portuguese were so dumb that Columbus came to the king in Portugal and said, well, you know, I have this idea, if we go this way, we can reach to India. Instead of going this way, going this way, we get there. And the Portuguese said, I don't believe it. They went to Spain, and yes, they gave him some ships, and he came to the Americas. And when he started going back, he noticed that if he would take a northern path, arriving in Lisbon, would be better if he would go the same way he came. And afterwards, they start doing this in such a way that they would come from here to here, and then would return this way. So they start doing that, knowing that the ocean was moving that way, but they couldn't explain why. And the explanation took a little longer. Actually, the first guy that tried to not understand, but at least summarize the knowledge was Benjamin Franklin. This is the first map showing the Gulf Stream, this kind of current that goes from North America to Europe. And that was what the ships from America to England or to Europe used to take in those times. But they couldn't explain why. Brazil was found by a Portuguese named Pedro Cabral, and this guy started again in Lisbon, and he came south. He stopped in Cabo Verde or Cape Verde or whatever. And then from this point, he wanted to go to India, but instead of coming this way, he did that. He actually ended up in India and returned to Portugal. But he was the first guy, at least that is in record, that came to Brazil. And after him, this was more or less the route that the Portuguese took for getting to India, because they knew more or less that the ocean was circulating here in the south of Atlantic this way. So they would take advantage of the circulation. This is kind of interesting because to show how the ocean moves, there are several ways for doing that. For instance, this is serious. There was a time that people would take bottles, put some notes inside the bottles, close it, and throw it in the ocean. In this notes, it would say, if you find me, please write me back saying where you found it, when you found it. And then the guy would say, well, I released the bottle in this position, and in a certain amount of time, it reached that position. So I would guess that the bottle went from here to there by the ocean, drifting in the ocean. So the ocean current is probably this much meters per second because of this. And this is something that sometimes happens by accident. There was a moment that a ship coming from Asia to the United States during a storm, it sunk here, releasing almost 30,000 rubber ducks and other stuff into the ocean. And then these little guys started being found in several places, like for instance, in Scandinavia, in Iceland, in the west coast of the United States, in Chile, and so on. So that was, of course, used as an indicator of how the ocean moves in general. Of course, at this moment I have to say, if you still believe that Earth is a flat disk, you have to leave, because what I'm going to say from now on depends crucially of Earth being a sphere rotating. Otherwise, my theory would blow up. I can't explain how the ocean moves in an environment such as this. Okay, so okay, we know that the ocean moves, and we guess that it depends on some forcing, some agents giving energy. And of course we know that in our planet, any energy related to any kind of motion in the atmosphere or in the ocean has to be given by the sun. So the sun is the main driver or agent providing the energy for the motion. And of course, because of the differential way this energy is being put in the system, it generates gradients. Gradients meaning differences between one place and the other. One place is warmer than the other, because if it's warmer, it evaporates more, and then the water gets saltier. So combining higher temperature and higher density, you have higher salinity. You have a different density than other places where you have different temperatures or salinity. And because there are differences in density, from one place there is a pressure towards the other place, and this results in movement. Of course, the atmosphere is something that is suffering the same processes, but when the atmosphere moves, it's starting kind of arresting or making some action over the ocean surface, and the water moves because of the wind. And also there is the gravity. Earth has gravity. The sun also attracts Earth and attracts the water. So gravity is another forcing, important forcing. And there is another one that is named the Coriolis effect. And this is what I say, that if Earth is not a sphere rotating, you cannot have this effect. And if you don't have this effect, the ocean circulation would be quite different than what the Vikings, what the Portuguese, what Columbus, or any other people that used to take advantage of the currents used to do in the past. So I'm saying that because sometimes it's difficult to argue with people that believe in certain kind of, it's not a religion, but I can't explain how someone in the 21st century still believes that Earth is not a globe, but there are. And on the other hand, we know, and people used to know from a long time, that the ocean moves in a way that is the way we know. But you can't explain that if you don't have Earth as a globe. So, and what is the Coriolis effect? The Coriolis effect is an effect that is due to the fact that the Earth is spherical, and when you have a sphere rotating, and any point over the surface, you can define what we call a tangential velocity. It's a velocity that points in the direction that point is moving, and it varies with latitude. In the equator, the velocity of a point is higher than in a higher latitude. So if you go, for instance, from the equator to the North Pole, any point that you take along this line, along this arrow, is moving slower than a point on the equator. But if you take a cannon or if you kick a ball on the equator in the direction of the North Pole, this ball has the tangential velocity on the equator. And as it moves north, it will continue with this velocity. But the Earth velocity, the point that is going to arrive, is slower. And in the end, someone observing this on Earth would think that the ball is taking this trajectory. Okay, lots of people don't get this explanation. I myself took a long time to get to understanding it. But there's a simpler way to understand it. In any point on Earth's surface, other than the equator, if you get something and throw it, it will move, but not in a straight line. It will move in such a way that in the northern hemisphere, it will be turned to the right, slowly turned to the right. In the southern hemisphere, it will move to the left. So if you throw a ball in direction of the northern hemisphere from the equator, this is the trajectory that the ball will take. It's going to be deflected to the right in the northern hemisphere and to the left in the southern hemisphere. And this is a very simple physical phenomenon that is easily explainable, but it takes a little while to really understand, so don't matter. Just believe me. If you don't, I'll do an experiment. I'm looking for the ugliest guy in the audience. Yeah, that guy. Okay, in which hemisphere we are? We are in the southern or northern hemisphere? Southern hemisphere. So if I want to hit your forehead, I'm aiming on your forehead. Oh, wait a minute. Earth is rotating, and I know that this is going to be turned to the left, so I'm going to take it north, because then it's going to do this. And if you don't believe me, because of course I'm not strong enough to send this with a high velocity enough to feel the, because this is a very small, large-scale type of phenomenon. But if you take a rifle, one of those very North American, usually North American used to kill their presidents. If you take it at 1,000 meter distance, I tell you, if you aim directly on the blank, you won't reach it. You have to, if you are in the northern hemisphere, for the guy that killed Kennedy, he aimed at Jacqueline Onassis that was on his side. I'm kidding, but this is something that really happens. And because of this phenomenon, the circulation of the ocean has the way it is. Of course, this is not a class on physical oceanography. This is just to give you some hints. And you can believe the Coriolis effect is something that really happens, and this is related to the Earth rotation. And there is a phenomenon that's very, very important in the environmental process, in biological processes, that what we call the Ekman spiral. The Ekman spiral is something that was discovered by this guy named Ekman. And the discovery was, it's interesting, I'm going to tell you. In the beginning of the 20th century, there were several people trying to reach the Northern Pole. No one had reached the Northern Pole by that time. For one reason, the Northern Pole is water. It's ice water. There is ice. In order to get there, you had to go with a ship. But the problem, the ship would take too long, and then before, the ship would never get to the Northern Pole, but you have to get closer enough, and then from that point, walk on the ice until you get to the Northern Pole. But the problem is that the ship would come from, let's say, from England or from Germany, whatever. And then when the ship arrives near the pole enough for they walking to the Northern Pole, the winter would come and freeze all the water, and the ship that was there would just be smashed down, because when water freezes, it increases in volume. So the ship that was caught, all right, thank you, would just be smashed. And then there was an oceanographer from Norway named Nansen. Nansen built a ship named Fram that was strong enough to resist to the winter in the northern regions. And he went with this ship, and the winter came, and all the water froze around the ship, and then he stayed there. He wasn't killed. For the first time, a ship resisted that phenomenon. And then he went to the North Pole and had fun. Probably had lots of whiskey for affording the winter. And then when the next spring came and everything started melting, a very large block of ice broke from the ice sheet, but the ship was held inside this block, or in the middle of this block. He couldn't do anything but just left the wind drift. And he was a scientist. He started marking the points where he was, measuring the wind, and was putting all the track on a chart. And then suddenly, wait a minute. The wind is blowing this direction, but the ship is drifting in this direction. And he started measuring. So I'm doing something wrong. No. And start getting very precise. And in the end, he saw that although the wind was predominantly blowing in this direction, the ship was drifting, or the iceberg was drifting at more or less 45 degrees to the right of the wind. And he could explain that because, wait a minute, is the wind that is pushing the iceberg? Why is that the iceberg is doing it? He couldn't explain. So he wrote to this Ekman guy that was a German, very good in calculation, and he found the answer. So there was an explanation, and of course I won't waste my time saying that here. But he said, well, what's happening is that because of the combination of different factors, when the wind blows in this direction in the northern hemisphere, anything that is on the surface of the ocean will move at 45 degrees to the west, to the right in the northern hemisphere, or to the left on the southern hemisphere. And this is something that we know today. For instance, if you try to have fun with your girlfriend or your boyfriend in the ocean in a boat, and because of the fun day, you forget about where you are, and then the gasoline or the oil goes, I don't know, something happened and you stay there, drifting in the ocean. And then people will try to find you. What is the first thing that we do when we go to find someone that is lost in the ocean? And to check how is the wind. So, well, this guy, they were, the last time we heard from them, they were in this position, and from then until now, the wind was blowing in this direction. So you have to, this is for you having a better chance of finding, or you that is lost having a better chance of being found. So we oceanographers know that if the wind was blowing this direction, and if you are in the southern hemisphere, we won't look for them in this area here, because probably they won't be here. We have to look in this part here, because probably the higher chance of finding them is looking in a region that's more or less 45 degrees to the left, to the wind direction. And this is something that is today used in practice. Okay, so the Ekman spiral, just to finish, the Ekman spiral is something that happens in the ocean, and happens in such a way that it helps to bring water from deeper regions to the surface. If you don't have this type of motion, the water in the ocean would be completely lifeless. Because for having life, you have to have food. And the food, the nutrients in the ocean are most of them in the deeper regions. Because what is nutrient in the ocean? Well, you have a green ball that does photosynthesis and stores energy. But for doing photosynthesis, has to have some nutrients around. And then when it does a photosynthesis, a little bug comes and eats the green ball. And when the bug is eaten by another fish, or the other fish eats another fish, there is always some left over that sinks to the depth of the ocean. When something dies in the ocean, it goes down. And this is nutrient. If you don't have any way to bring up this nutrient that is accumulated in the deeper regions, in the end you don't have nutrients. Even if you have sunlight, if you have green ball, but you don't have nutrient, the green ball dies, and the little bug that eats the green ball dies, and you don't have life in the ocean. So in order to have this, you have to have upwelling. You have to have resuspension of water. And the Ekman spiral is one of the most important agents in doing this sort of redisponibilization of nutrients in the euphotic zones where life is sustained. Well, according to my watch, is 11, and I stop here, and then we continue from this point on.